So for the second part of this lecture, we will discuss the pressure variation for the compressible fluid. So compressible means you can compress the fluid. That means you can change the volume. That means this volume can be changed. That means gamma is not constant. And example, any gases can be the compressible fluid. So if we can remember what was the pressure variation in vertical direction, that was dP over dz negative gamma. Now here again we can start the axis from top to bottom, like from down from top to downward or from bottom to upward direction. So I will keep that as it is here, that is z equals to 0 or z. Okay, so here since gamma is not constant, so we need to do some extra steps. So I will just write down this way, and integration sign. Now since gamma is not constant and it's for gas, obviously we need to use the ideal gas law. So the ideal gas law was, if you can remember, it was P equals to rho R T. P and T were absolute, R was the ideal gas constant and rho was the density. Now here we are using gamma and here the equation is in density. So what we can do, at first we can find the expression for the gamma and the density, and then we know gamma equals to rho times G. So P G R T. Okay, so finally gamma equals to P G R T. So that's what we can use here, dP negative P G R T delta C. Okay, now if the situation is something like that, the temperature is constant, then we can say this T is constant, or the isotherm condition. Okay, so the isotherm condition, and G is constant also, R is the ideal gas law, so ideal gas law constant, so R is so constant for each gas also. So what we can do, we can just rearrange this equation. Since P and P on both sides, I will bring both P on the same side, and here what I will do, here I will take the G and RT outside of the integration sign, because all of them are constant, provided here we are using the isotherm condition where temperature is constant. Okay, if we use that, then T is constant here. Then if you do, and we need the limit. So here limit can be what? P at this point, P will be P naught, and or like here P will be P naught, and and here P equals to P. At this point Z equals to Z naught, at this point Z equals to Z. So what we can do, from P naught to P, here from Z naught to Z. Okay, can do that. And from our integration knowledge, we know dP over P, which is actually the ln P. So P over P naught, and here since G RT Z naught C, if I go to the next slide, it will be again ln, I'm just writing that the previous line again, G RT Z naught C. So ln P over P naught minus G RT C minus C naught. Since we are interested about P, so I will try to remove the ln. If I take ln from this side to other side, it will be e to the power G RT Z minus Z naught. So P will be P naught E G RT Z minus Z naught. Okay, and that is the equation or the characteristics. It will represent the pressure variation in the vertical direction for the compressible fluid. Okay, so that is the equation for the compressible fluid. Now here once we know the Z and Z naught and for what type of gas we are dealing with, that will give us the R. We know the G. Once we know the P naught, we can actually calculate at any place if we know the temperature and pressure, everything on that point. Okay, so that's what we will do for our homework. The class example 6. Class example 6, you can find that in Canvas here. So the class example 6, it says that for US, as this is a picture of the standard atmosphere in here and with the temperature, and you can see at different level the temperature is different. So what they are saying, the question is, what is the pressure at Z equals to 15 kilometer when the temperature is 56.5 degrees Celsius, given that the pressure at 11 kilometer is 22.5 kilopascal and the ideal gas constant for air is 286.9 joule per kg Kelvin. Okay, so we have to find the pressure at somewhere here, which is 16 kilometer from here. Now, and the temperature at that point is 56.5. Okay, we know the temperature, which is good. Now, if you look at the total picture from this point to this point, there is temperature variation. From this point, this point, this point, this point, there is temperature variation. So the only part where there is no temperature variation is this one. So at this part, the equation we just developed, that can be used, and that's what we will do. So let's write down all the given values and what we need to find. Okay, so given values, the first thing is Z equals to 15 kilometer, and if you look at the point from where that constant temperature started, that is actually 11. So what I will do, I will name that point as Z naught here. and this is Z, which is 11 kilometer. Okay, now temperature is negative 56.5 degrees centigrade and pressure at Z. So if we go to the previous one, that P naught is the pressure for Z naught. So here, since Z naught is 11, we will say P naught equals to 22.58 kilopascal, and we know the R, which is 286.9 joule per kg Kelvin. Okay, these are the given values, and we need to find the pressure at 16, which is P, only P. Okay, now few things here. We know we have to convert every parameter into the standard unit. Now everything is in kilometer, kilopascal, so we know it will be 10 to the power, like 15 10 to the power 3 meter, 11 10 to the power. So let's change that. Here it will be 15 10 to the power 3 meter, 11 10 to the power 3 meter. Here 22.58 10 to the power 3 pascal. Now one thing here, the temperature here is 56.5 degrees Celsius. We need to convert that into the standard scale, which is Kelvin. So what we will do, negative 56.5 plus 273. So that will be, what will be that? 216.5 Kelvin. Okay, now everything is in standard unit and we are ready to use that in our equation. Okay, so here the solution for compressible gas, P equals to P naught E and G R T Z minus C naught. Okay, now if I go to the previous one, here the pressure is P naught 22.58 and we need to find the pressure at this point. Okay, so we know this one is 22.58 10 to the power 3 E, G is 9.81, R is 286.9 to 16.5, and now we need to find Z to Z naught. So here Z was what? Z was 15 and Z was actually 15 10 to the power 3 minus 11 10 to the power 3. Okay, and now if you do all the calculation properly here, I'm just writing the very final answer, which is 12 into 10 to the power 3 pascal, which is 12 kilopascal here. That means at 11 kilometer elevation from the ground surface, the pressure will be 12 kilopascal. Okay, so that is the end of our lecture 9. You will find both of these videos on YouTube. Thank you very much, and I will see you on Wednesday.